All right. This is the lecture recording for Wednesday, February 18th. So this week we're doing approximation algorithms. I think it'll be on the shorter side as a lecture, but at the same time, I've beefed up this week's course of study, so you should have plenty to work from. Since I won't be here, you can email me. You can also email me and we can find a time to chat on Zoom. So just let me know. So this week we're doing approximation algorithms. In particular, we're going to focus mainly on really, really good approximation algorithms, something called a polynomial time approximation scheme. And I want to give you a heads up at the beginning that this week, the odd week course of study, which I think is the one that'll take you longer, is theory heavy and involves mostly reading a paper. Whereas the even week course of study is implementation heavy. You're actually going to implement an algorithm. So if you are somebody who really likes the theory side or the implementation side, go ahead and let me know, and you and your team can swap if you'd like to for this week only. Um, all right, so we're going to cover approximation algorithms and a little bit of the complexity theory around them, a couple of definitions, a great widely used technique, approximation by rounding. Basically, whenever you're solving a numerical problem, you can round the input numbers and solve a coarse-grained version of the same problem faster. And finally, we'll talk a little bit about approximation algorithms for the traveling salesman problem. All right, approximation algorithms. So the other day we saw this slide and we saw tactic two, which is if you can't solve the really hard problem, one thing you can do is find a pretty good solution. That is, it may not be optimal, but hopefully it's provably within some factor of optimal. And this works for a lot of really hard problems, but not all of them. So in particular, there's a complexity class called APX, which captures all optimization problems whose decision variants are in NP. So that includes traveling salesmen, for instance. And the optimization variants can be approximated in polynomial time to within some constant factor. So like a 2 approximation or a 10 approximation or a 1.1 approximation. So in particular, we've already seen a 2 approximation algorithm for the traveling salesman problem in metric spaces where the triangle inequality holds. So this is the thing we saw where we can efficiently find a minimum spanning tree. We can construct an awkward tour by walking around the minimum spanning tree, and then we can relax that awkward tour to find a greedy traveling salesman tour that is within a 2-factor of optimal. So another way to say this is that we were previously able to prove that metric TSP is a member of the class APX. There we go. My annotation's working. However, we can do better than constant factor approximation, or we can do arbitrarily good constant factor approximation. So one thing that I think is really surprising is that a lot of extremely hard optimization problems can be approximated arbitrarily well. That is, to a factor of 1 plus epsilon for any constant epsilon in polynomial time, which if you sit with that for a second should strike you as a crazy thing because essentially we're saying I can get you as good of an approximation as you want. A 1.00001 approximation we could get. And the catch is that fixing epsilon determines how long your algorithm will take to run. So you can get an arbitrarily good approximation factor, but at the same time, the smaller epsilon is, the greater your runtime is. So as you go to that 1.00001 approximation, you're also going to maybe an n to the 1000 time algorithm. So formally, we call this a polynomial time approximation scheme. And this is some algorithm which takes as input this parameter epsilon and gives you a 1 plus epsilon approximation in time n to some function of 1 over epsilon. So as an example, if you got, for instance, a 1 plus epsilon approximation in time, I don't know, n to the power of 1 over epsilon, we can imagine you can get your 1.001 approximation, but that would also mean you're dealing with an n to the 1 divided by 0.001 time algorithm, which would be like an n to the 1,000 time algorithm. So for any fixed constant, you get a fixed polynomial, but those polynomials might grow really badly. And in particular, notice that I haven't specifically told you how the runtime depends on epsilon. So like everything else in complexity theory, you can break this down almost arbitrarily far. So if you want to get further into sort of fine-grained variations on polynomial time approximation schemes, EPTASes, also known as efficient polynomial time approximation schemes, well, we now know the word fixed parameter tractable. If we treat epsilon as a parameter, these problems are fixed parameter tractable with respect to epsilon, which means um, they're going to run in time some function of 1 over epsilon times some polynomial in n. So as epsilon grows, it doesn't change the polynomial, although it still might grow like super exponentially in 1 over epsilon. Um, and then finally, a fully polynomial time approximation scheme is fast in both 1 over epsilon and polynomial and n. So for a fully polynomial time approximation scheme, you'll have 1 over epsilon to some polynomial times n to some polynomial, which essentially means as you increase n or shrink epsilon, your runtime grows in kind of a more reasonable way. But I do want to stress just how great these approximation algorithms are. You can get really, really good approximations. Let's see a couple of them. So one kind of approximation scheme, a general strategy that works for a lot of numerical problems is, well, if you want to figure something out about a bunch of numbers, round the numbers so they're essentially smaller, and then run the algorithm on the rounded numbers. So we've already seen subset sum in this class. I think we had a slide very much like this before. So to remind you, in subset sum world, we're given a bucket of numbers, we have some target, and we're looking for a subset of numbers that adds to the target. So in particular, we saw a dynamic programming algorithm that ran in time n times t, where n is the number of input numbers and t is both the target and effectively an upper bound on the size of any of the inputs. So this is a decent algorithm as long as t is small, but t could be enormously big, and in the past we've worried about that possibility. But one thing we can do is we can effectively make t small just by choosing to round all of these numbers. So here's how you get a fully polynomial time approximation scheme for subset sum with a little rounding trick. We have our big O of nt algorithm. So that's set, that's something we can do, solve the problem in time big O of nt. We'll take our input, we'll say we have n numbers, a1 through an, some target t, and a parameter epsilon that's some constant greater than 0. So on the right-hand side here, I've got an example instance, and we can imagine these are all of our numbers, and maybe just to have some reasonable numbers to play with, we'll say n equals 100, and epsilon is 0.01. So we want an approximation to within 1% of the optimal solution. So running this algorithm, if we didn't change the input numbers, would have a runtime that depended on our target, which in this case would be on the order of 1,000,000. But the other thing we could do is we can just round each number to the nearest multiple of epsilon over n times the largest possible input. So in particular, here we've got epsilon over n is 1/1000th. So we'll round each number to the nearest multiple of 1/1000th of the largest input number. If the largest input number is 1,000,000, then we're just rounding all of these input numbers to the nearest 1,000. And now I claim that all the numbers are now effectively integers in the range between 0 and n over epsilon. because essentially we rounded all of these numbers to one of 1,000 values. So if we wanted to, for instance, ignore these last three zeros, we could just scale the inputs down because we've already rounded them. So the size of our largest input is now much smaller. So if we want to calculate our runtime, it's now big O of nt, but t has become n over epsilon. Um, sorry, n over epsilon times n input numbers. So this runtime turns into n numbers times every number upper bounded by n over epsilon times t is an upper bound on the sum of all the numbers, which gives us n cubed over epsilon. And you can optimize this. This is not necessarily the optimal relationship between n and epsilon, but the point is just this lets you get, for any epsilon you want, a polynomial time algorithm that solves the problem within an epsilon factor. So that's neat. Um, and this is what even teams are going to be doing for their implementation this week. They're going to do the variant of this algorithm, except implement it for the knapsack problem, which is similar to subset sum. The trick is exactly the same. And if you want to, there's actually one more neat approximation algorithm that is in the course of study. And if you want to implement multiple and see how they work in comparison to each other, you are more than welcome to do that. Oh, and if we want to bound the total additive error from our rounding, well, every time we choose a number, we're off by at most 500 if we've rounded to the nearest 1,000. So if I'm being lazy, well, then at most I'm losing an epsilon fraction of my largest number. So epsilon over n times n numbers. All right. Second piece, how hard is approximating the traveling salesman problem? We already saw a decent approximation algorithm for metric TSP, but general TSP turns out to be really hard to approximate. And there's actually a nice proof that comes from the NP completeness of this problem and from its relationship to Hamiltonian cycle. So as a reminder, Hamiltonian cycle is sort of like TSP without edge weights. You're given some graph and you want to find a cycle that visits every vertex exactly once within the set of edges that are on the graph. So let's assume for contradiction that you have a nice C approximation algorithm for the TSP problem for some constant C, maybe a 100 approximation algorithm, which doesn't seem too unreasonable, right? Something within 100 times the fastest possible path. Well, if we had such an algorithm, this would give us a contradiction. And the way to think about it is this. Give me an instance of Hamiltonian cycle. So I'll have edges in my Hamiltonian cycle. I'm going to turn this into a TSP instance, so I'll set all of the existing edges to have weight 1 and all the non-edges to have weight Cn plus 1. So essentially, if my TSP tour uses anything that was a non-edge in the Hamiltonian cycle instance, it's horrendously expensive. Good Hamiltonian cycles will turn into TSP tours with weight, total weight n. And any other TSP tour will have total weight at least Cn plus 1 because it'll use a non-edge somewhere. So all we need to get a result is to observe that if we can get a 100 approximation to a TSP tour, the only things in this instance that approximate an optimal TSP tour is Hamiltonian cycles themselves. So approximately solving the problem, in this case, getting anywhere close to an optimal solution means we must have found the optimal solution. So in other words, if we could get a constant factor approximation for general TSP, we could solve Hamiltonian cycle in polynomial time, and that would contradict the fact that we know Hamiltonian cycle is NP complete. So if you really like symbols, you can write this result purely in symbolic terms. If P does not equal NP, that implies that TSP does not admit a constant factor approximation. But, and here is the super cool result that odd teams are going to spend their weekends trying to puzzle through. It turns out there is a 1 plus epsilon approximation for Euclidean TSP, meaning it has a polynomial time approximation scheme, which puts a really interesting um, difference between these three versions of the problem. For Euclidean TSP, we can get an arbitrarily close constant factor approximation, any constant you want. For metric TSP, the best we can do turns out to be, at the moment, just very slightly better than 3/2 approximation. So a decent constant factor approximation, but nowhere near to an arbitrarily good constant factor approximation. And then for fully general TSP with no metric assumption, you can't approximate it to any constant factor at all, which is a fascinating split between these three versions of problems that seem very similar. So the polynomial time approximation scheme for Euclidean TSP, this is a result that was worked out in the late 90s by Aurora and Mitchell. It won them the Gödel Prize, which is the highest prize in theoretical computer science. It's the closest that theoretical computer science has to a Nobel, although there's still the Turing Award for computer science in general. Um, the proof is tricky. Like the write-up I'm going to give you is pretty much a research level write-up, but it's a pretty good write-up. And I've also given you an overview summary and some alternative documents to help you make sense of it. And I think it'll be really rewarding to work through how the approach works. Um, but strategies as you go through and try to follow this proof. Strategy one, like always, break things into pieces. Take the proof step by step. Try to convince yourself that one step works before you try to convince yourself that the next step works. Work top down similarly. So get a high level sense of how the algorithm works, take lemmas for granted, and then come back to how those specific lemmas and low level pieces work later. Draw pictures. Whenever you're working with graph algorithms, draw pictures. They almost always help. And you'll have multiple sets of lecture notes that I've also posted on the course of study and the Canvas. I couldn't find any lecture notes that I was fully happy with. They all have some flaw or another, which is why I've given you a write-up by Aurora. But put together, they offer a pretty comprehensive coverage of how this algorithm works. So let's at least sketch it. I want to give you the idea of how it works so you know what you're dealing with when you read up the formal write-up. So step one for Euclidean TSP, our input is going to be a bunch of points in Euclidean space. And for this week, we're just going to focus on two-dimensional Euclidean space. So our input is a whole bunch of points in the plane. And the first trick we're going to use is the same trick we used for subset sum. We're just going to round all the points to the nearest coordinates in a really tightly grained grid. And how tight grained this grid is will depend on how good of an approximation we want. But this will have the nice effect of essentially giving all of our inputs integer-like coordinates on any scale of integers we choose based on how we scale this grid. And another nice thing about this is that if we solve the rounded problem, we actually have a solution that's guaranteed to be not too far from the solution to the original problem. Reason being, if I have some solution to the rounded problem, let's say maybe my solution goes from this point to this point to this point to this point, and so on, I can actually change this into a TSP tour that works for the original instance by saying, all right, I'll just make a little excursion from each of the rounded points to touch the actual point. And by the triangle equality, that excursion is an upper bound on how badly off my actual result is. So once I've rounded things, the second thing I'm going to do is I'm going to take my grid and dissect it into little squares. So in particular, I'm going to decompose the space recursively. So I'll have a bounding box that contains the whole instance. I'll break that into 4 pieces, 4 quadrants of equal size. I'll break the quadrants into quadrants, and so on all the way down. So if you're familiar with a quad tree or other ways of representing decomposing space, you can think of this recursive decomposition as just a tree with branching factor 4, which lets you navigate between the different geometric regions pretty efficiently. So now what we have is we have a grid with some really tight grid lines. We've got points rounded to those grid lines, and we've recursively broken the grid down into really small pieces. The last piece of complexity that we might have to worry about is even in a really tiny grid square, um, we're still working on the real plane. So your optimal TSP tour might cross at all sorts of different places, an arbitrary number of different places and an arbitrary number of times. So the next simplification we're going to make is we're going to, for every box, define a lot of special points, special entry and exit points on the edges of each box. And we'll say, these points are portals, and my TSP tour is only allowed to enter and leave the box through a portal. So what this means effectively is that we are losing some fidelity again. So it's not necessarily true that the actual optimal tour goes through these portals, but like we did with the rounding, we can bound how far off we have to fix our TSP tour to actually make it work. So if our optimal TSP tour doesn't go through a portal, well, our portal restricted tour, if the portals are close together, loses at most some amount of distance that we can bound. So why are portals handy? Portals are handy because they give us a finite state space to look through when we want to solve this problem on the smaller boxes and then work back up the tree of boxes via dynamic programming. So in particular, let's imagine our path goes through each portal a constant number of times. So maybe our optimal path goes out this portal, and then in this portal, and then out that portal, and then in this portal. It's not really a portal, there we go. And so on. Um, which portals are used is some function of m, if there's like m portals. So if there's m portals in total, which ones we use, there's like 2 to the m possibilities for that. How many times they're used? Well, if we assume they're all used a constant number of times, the number of times they're used, possibilities for that is also bounded by some function of m. Whether they're used going into or coming out of the tiny box, that's a function of m. That's like another 2 to the m choices for our entries and exits, and then the order in which we enter and exit the box. So what this means is that the total number of ways for each box that we can enter and exit it through portals in any specific order is something that we can bound and enumerate through. So essentially, for each box, we're going to solve this subproblem dictated by the way the path enters and exits our box, and we're going to store solutions for all of the subproblems. Once we've stored solutions for all of the subproblems, then we will combine the best solutions for each of the 4 component boxes. That is, we'll look through all quadruples of optimal solutions that require our path to enter and leave these sub-boxes in specific places. We'll then look at all the quadruples that are compatible with each other, meaning the path exits one box right before it enters the other box, and then we will compute the best solution from all of those, which will give us essentially our solution for the next level of boxes up. So we'll do that repeatedly, and we'll store many solutions for all possible configurations of entering and exiting this box one level up, and then we'll work up to the next level and up to the next level, all the way up to the top of a recursive tree. So to recap what we're doing, we're working in the plane, 2-dimensional Euclidean space, although we can generalize this to d dimensions. We start by taking our input points and rounding them so that we've essentially got manageably sized points with reasonable integer-sized relationships to each other. Then we decompose this space so we can talk about solving tiny subproblems and then recursively combining those solutions to get the solutions to larger subproblems. We restrict the number of ways our TSP tour can interact with each box by using portals and enumerating all of the ways that any TSP tour can possibly interact with the edges of the box before solving that subproblem for all possible subproblems in all of the boxes. And then we repeatedly combine our optimal solutions for the various little boxes to get the solutions for larger boxes. Now, there's a lot of parts of that analysis that I have left out, so um, that will be your major task for this week. All of the problems for odd teams are essentially tasks of explaining something in the reading that's a little bit obscure or a little bit fast. So I hope you'll find it really exciting and interesting. Um, as a reminder, odd teams are going to do this heavy proof exercise. So if you want to read research level algorithms, be an odd team. If you want to do cool implementation, be an even team. And I'm happy to let your team swap for this week. So let me know if you want that to happen. I won't be here on Wednesday, Thursday, Friday. That includes my office hours, but I'll be on email and you can always ping me if you want to schedule a Zoom check-in either during the week or even over the weekend. So that's all for today. Thank you guys very much.